Okay, let's revisit stability. This is in section 2.6 of your book. Talks about system stability. We've talked about this in the past in terms of bounded input, bounded output stability. And it can be shown that this definition of stability that we've used in the past is equivalent to a condition on the impulse response. And that is if the impulse response is what's called absolutely integrable, if we can integrate the absolute value of the impulse response over all time, and then that is finite, then the system is bounded input, bounded output stable. If this is infinite, if the integral of the absolute value of the impulse response is infinite, then it's Bibo unstable. So just a couple of quick examples based on some of the impulse responses that we've encountered. If h of t is of the form e to the minus 2t u of t, then this is a decaying exponential, and it is bounded input, bounded output stable. Similarly, another example would be an impulse response of the form of e to the minus 2t plus e to the t u of t. This is Bibo unstable because of the increasing exponential term. So if you integrate that from minus infinity to infinity, you would get an infinite result. Another example would be an impulse response of the form sine of 3t u of t. Now, if you integrate over this, you over just h of t, you would expect to get on average 0, but remember we're integrating over the absolute value of h of t. So we would just keep adding area. So again, this would be an example of a system that's Bibo unstable. So let's take a look at another definition of stability, and that's asymptotic stability. And this definition doesn't put any conditions on the input, for example, that the input be bounded. It only depends on the position, the location of the characteristic roots of the characteristic equation. And a system is stable if all the characteristic roots are in the left half plane. So mathematically we can say that if the real part of all the lambda I are negative or less than 0, then we've got a stable system. So examples would be, lambda I equal minus 2, or in the complex form, minus half plus j3, and so on and so forth. As long as the real part is negative, then the system is stable. Another way to say this is that all of the roots of the characteristic equation lie in the left half of the S-plane. So if I sketch the S-plane, this is the real part, this is the real axis, so this is the real part of lambda. This is the imaginary part of lambda. Okay. If I have poles located anywhere over here on this side of the real part of lambda equal to 0 axis, any lambda values that have real part less than 0, then they're negative. The modes are going to have be decaying exponentials. So, and this is the left half plane. This is the right half plane. Okay. The left half plane is this entire region here. The right half plane is this entire region here. A system is unstable if the real part of any of the characteristic roots is positive. So again, any lambda I with a +3 or plus 0.25, or of the form 1/2 minus J7. As long as the real part of the root is positive, the system is asymptotically unstable. There's a third condition we call marginally stable. And in marginal stability, this is where the real part of any of the characteristic roots is equal to 0. So this would correspond to any of roots lying exactly on that vertical axis in the complex plane. So again, lambda equals 0 would be 1, or J3. And as long as the real part is 0, then this would correspond to a marginally system. And for the system to be stable, all of the characteristic roots have to have negative real parts. A system is unstable if any of the roots are in the right half plane. A system is marginally stable if any of the roots lie on the imaginary axis.